Hi guys, hope you're all doing well. Okay, so we're going to be building a pulse motor using a bucking field with steel stators on the rotor instead of magnets, and this project is about making a setup where we can try different configurations and get some questions answered, I guess. So these transformers you see here contain the E-cores we're going to need for this pulse motor build, and these are the Lee & Long Deluxe Universal AC/DC adapter 1500 milliamps. It has variable voltage outputs 3, 4.5, 6, 7.5, 9 and 12, and a maximum output current of 1500 milliamps apparently. So I have maybe around 200 of these particular ones and a couple of hundred of other various ones, and the way I came about those was my employer actually imports these from China, the old cheapo stuff by the container load, and 3 pallet loads of these types of transformers came across. There's this one here, a 3000 milliamp model, and a 120 to 240 converter transformer, and they all came across with the wrong plugs on the input leads, so will not plug into our grid power here in Australia. So the boss rang the company that he got them from. The company said basically, well, throw them in the bin because it'll cost us more to ship them back than what they're actually worth. So bit of love talk, and I managed to score all of these transformers for a sum of nothing. A little bit of a product review we'll do while we're going here. This one, when I opened, I found that the little sticker or pad or whatever that clips on the front had actually fallen off. This one here I found when I opened it and pulled it out of the box, came with spare parts hanging out the side. That looks like the little slide disc that goes under the forward reversing switch here. And this one that I took apart so we could have a look inside and see how they are actually set up and see how cheap and nasty they really are, came with track repairs on the printed circuit board before it was even shipped out. So remember, none of these have been used, they're all brand new. So there you go, 2 of the tracks have been repaired, and looking at that, it is the 3 and the 4.5 volt side. Yes, so there you go. That came over with some, the soldering is quite dodgy on that too. In fact, it doesn't even look like it's joined where it's supposed to join. Get a close shot of that wonderful repair work. But I guess the amount they get paid over there represents the quality of the work they do. You pay peanuts, you get monkeys. Right, so what can we get from this? Well, we got the E-cores here, and these ones come apart quite easily, which is good for us. We're actually going to have to pull 3 transformers apart to get enough E-core segments to fill up 2 bobbins, as some of these are just strips that fill in the blanks. We get a capacitor, 25 volts, 2200 microfarads. We've got a multi-selection switch here, a red LED, and a reverse forward current switch, or power flow, reverses the polarity of the output as they are an isolation transformer. So that's basically about it. We've got our 4 little diodes here that make up our 4-wave bridge rectifier. We have this diode here that is actually directly across the cap, as you can see. So that there is the 2 cap terminals, that there is the 2 diode terminal, the resistor terminals, sorry. So that resistor is directly across the cap, so I'm guessing it's their attempt at bringing the peak-to-peak voltage down that would normally charge that cap to some sort of RMS value. But there you have it, and another little resistor there that's coming off the 3.5 volt side going to the LED, so the LED doesn't overvolt. So that's basically it. We have primary winding on the top, secondary winding on the bottom, and nothing much more to it. They're stuck inside the transformers with a bit of inside the casings with a bit of double-sided tape, and you have your 4 different output jacks that hopefully fit something you got that you want to use the transformer for. So I found that these flash little U-butte things here that just sort of clipped over the LED fall off quite easy, and when you open the casing the whole thing falls out quite easily. So if we're really tight for money, I guess we could salvage these diodes, resistors, LED and capacitor. Although unfortunately with the capacitor they've chopped the legs off fairly tight against the printed circuit board, so you'll be dealing with the fact that you're only going to have a very short bit of wire to solder onto. But anyway, we don't want to use them for a transformer, we're going to use them for parts, and while we're here we'll simply open this one. Six screws, quite surprising actually. They're actually pretty solid. I mean, they're tight in the casing, well presented. I guess I could have stuck that down a bit better, but we're looking at a retail price of $12 for these. That's Australian dollars, so I guess we can't expect to receive some sort of Lamborghini. We're paying to buy a crappy old Jeep. One more, and we're there. That one was a bit tight. So there you go. That part sits in the bottom, which sits over there. No double-sided tape this time, must have ran short on it. Tip it up. This one is taped on, and once again we have the same deal. So that little plastic slide that was hanging out the side of the transformer isn't actually from this transformer because it's already got one on it. Basically much the same thing. So what we're going to do now is we're going to pull apart all these E-cores or transformer cores, and going to rip all the windings off. The secondary windings are no good to us. Turn ratio is too low for the voltages we want to be using. The primary is, turn ratio is too high for the voltages we're going to be using, so we'll have to rewind the coil. So no problem at all, we can do that, just a bit of time. So I'll go ahead, get all these apart, get the coils rewound, E-cores back in position, and then we'll come back and have a look and see what we got. But for $12 they look pretty neat. Like I said, they could have stuck the trim on a little better. It seems to just want to sort of click over the LED, and that's what you have. So yeah, if they had the right plug on it, $12, variable voltages. I have checked the voltage output and their out, each one, where it reads 3 volts would actually be about 3.5, so about 0.5 of a volt out on each setting, whereas the voltage is actually 0.5 volts higher. The polarity changeover switch works quite well. The LED shows us that our power is on, 1500 milliamps. I've actually loaded one up to 1800 milliamps, there's no fire. So there you go. I guess, yeah, for $12, not a bad deal. If you want a much more expensive transformer with some sort of voltage regulation other than a resistor across the capacitor, then you're going to pay a lot more, of course. Anyway, on with the project. Enough of the product review. Yeah, I guess it's worth its $12 really. If you've got devices that are a little bit tolerant to being either overvolted or undervolted. Okay, we'll be back when our cores are ready to go. Just before we do leave, this is what we're going to use for our rotor bearing. Haven't yet made a rotor, don't know what I'm going to do in regards to that. It'll probably just be a wooden one that sits over our shaft. And the reason we're using this stepper motor as our rotor bearing is actually going to use the generated output from the stepper motor to rectify and send to this cap with a set resistive load across that cap, and we're going to use our step resistor here, and this is just a series, a whole bunch of quarter watt resistors to each value on a rotor dial. So we'll just have that across the cap. We can place various different loads and read the voltages across the cap and see what kind of power output we can get as far as mechanical rotational output in regards to whatever load we place on our little generator. Okay, so time for the long slog, get these apart and rewound, put back together, and then we'll be back and have a look. Okay, an hour and a half later, thereabouts, we have our two coils made. Now you will see one has a chocky block with 4 terminals on it, and the other has chocky block with 6 terminals. So we'll run through what we've gone and done here. Okay, so you see we managed to end up with a very nice flat finish on each of our inductors. And what I've gone and done here in regards to windings is this coil here has 2 windings. Our front one is going to be our power or drive winding, and this rear one is going to be our inductive kickback collector. Now the reason I've done this, wound a separate coil to collect the inductive kickback, is because I can now electrically isolate this coil from the rest of the system. This gives me the option of either sending the inductive kickback to a load, or to a third inductor, or back to the source. Sending the inductive kickback from a primary back to the source is very hard when they are electrically connected. As most of you may know, in the Bedini SSG pulse motors, causes all sorts of problems. This way there is no problems. we can put the polarity around the correct way, rather than with the Bedini machine. You would normally have the negative side of the charged battery hooked to the positive side of the run battery. Works okay that way, but you try and send the inductive kick back to the positive side of the run battery and from the primary coil, and you run into all sorts of dramas. This way there's no dramas, so we can now choose to do whatever we want to do with our inductive kickback. Our power windings on both coils, the front windings is 150 turns of 0.55mm copper wire. Our inductive kickback coils on both inductors are 150 turns of 0.4mm wire. Okay, now the extra winding on this one here. Underneath the inductive kickback winding there is 50 turns of 0.4mm wire. That is going to be used to pulse our LED that we'll be using as a strobe light to see where our timing is in regards to the rotor's steel block to that of our bucking coils. Other than that, the inductive kickback and the power coil are both identical, and I have wound them so that they are in the same direction and the two coils are facing each other like so, and our rotor will be passing through the gap between the two. The chocky blocks instead of hard wiring, so I can change the polarity of the two drive coils, so as we can have it either in bucking mode or in standard mode, where one is north and one is south on this face, if we're going to use the north and south analogy, which we will. Makes things simple to understand. And it is also so I can either series or parallel connect the two coils. So that's probably the hardest bit of the build done. They're ready to go. The laminates are packed in there nice and tight, and the last one is actually hammered in each one, same amount on each side. So as far as our two drive coils are concerned, everything is even. The LED coil will be driving or pulsing the LED when our drive coil fires up, so it won't affect our inductive kickback when the drive coil is switched off, as the LED will just become a freewheeling diode. So of course the current will follow the path of least resistance, which of course is our inductive kickback winding. So even though one is a little larger than the other, the results between the two should be the same. So that's where we're at, and we're ready to take our bearing here and make a rotor, which of course is our stepper motor. Little info on it for you. Now I'm going to make a reasonably large rotor due to the fact that the stepper motor creates a fair bit of power at a slow RPM for what it is as far as power goes, and that is power output from our two sets of windings, which of course are nothing but lots of little inductors wound in series, and we have two sets of those, so we can have a single output or we can have a dual output. We'll see what happens when the time comes, how much we actually need. So the way we're going to set this up is going to be giving us the ability to calculate the mechanical energy minus whatever the efficiency is of this little here stepper motor being used as a generator, and also the efficiency of our inductors. So I'll just get our inductive meter here. I'll wrap it and do all that crap with one hand. And we'll take some measurements while we're on the fly here. I hate trying to work one-handed. That's probably going to be asked about my face, isn't it? Let's see, we'll start on the 20 millihenry scale. Okay, so first we'll try our power coil, which is in there. Oops. 2.73 millihenries. Our inductive kickback coil. 5.29 millihenries. Hopefully this one will be about the same. Our power coil. Oh. 2.67 millihenries. And what was this one again? 2.73, awfully close. And our inductive kickback coil in this case, which may be a little different due to the warning underneath it, that's 5.26, that is the one wound above our LED driving coil, and the one without the LED driving coil is 5.28. So we got 5.28. Well, it doesn't go much closer than that, and our little LED driving coil is 0.6 millihenries. So there you go. I wasn't looking through the camera, so I hope I had the meter in shot. Everything's fairly even, so we're ready to build a rotor for this thing, set up a base plate, mount L2, and get to it. That'll be in the next video. But for now, I'll go and get this all joined, converted and uploaded so you can see where we're at, and start doing some serious testing. Thanks guys.